Aloha, Richard Halverson here. This is ITS148, and today I'm going to do programming project 19.4. So let me share my screen. And we're going to do 19.4. So if we look at Pearson, here's chapter 19. 19.4 looks like this. And BST Iterator. So we have a class, or we have a BST class, and it comes with that in our code here, test code. And we're supposed to write a MyBST class that extends it, adding an iterator, okay, for traversing all the elements in increasing order, okay. So we're going to add an iterator to the BST class, and the iterator is going to be able to allow us to iterate through all the nodes in the binary search tree in order. So let's take a look at what this code looks like. Let's see, I got to grab it here. Copy, paste and go. And it's this code here, and they give us the binary search tree and blah, blah, blah. And then down here, begin Rebel submission, we need to we're creating this MyBST class, and we need to add this iterator. So we add this def iter line, and we have to write this class right here, this BST Iterator class, and that's going to go right here. So we're going to put our code here, and then we're going to submit this, including our code. Okay, so I'll tell you what, I'm going to Control A and copy all this and go to my blank here, and I'm going to paste it. So I'm talking about adding a BST iterator right here. Okay, so the question is, what is an iterator? Well, let's just do a really quick review here. If we go back to chapter 18, this is where we introduce linked lists, and linked lists are the first very commonly used data type that is not built in to Python. Okay, so a linked list is like a list, except for you cannot just iterate through it using an index, using 0, 1, 2, 3, 4. It doesn't work that way. What it does is you have to iterate through it by the next element in the list is information in the current element of the list. In other words, we have nodes of the list. We call them nodes now and not elements, because nodes contains more than just the element value. It also contains this other variable, which indicates what the next one in the list is, which points to the next node in the list. And so depending on how this whole list is implemented, now this is way at the meta level or whatever, but let's say it's a bunch of nodes and all the nodes themselves are indexed, so we can access each node directly if we want to, but we don't want the index to be the order, okay? We want to say what the order is what the next index is in the current index. And so so if it were a bunch of blank nodes that you can refer to them independently by an index, this value would be an index number, because it says the first one is at index 2, and the next one is at index 5, and the next one is at index 34 or whatever, back to 1. And so these nodes can be more or less out of order when you look at them from an indexing point of view, but they're not out of order in how you define your list. And so you still have to be able to do the same stuff: retrieve an element, insert a new element, delete an element, and so on. How many elements are on the list, whether an element is in the, you still have to be able to do all that stuff. But things like inserting a new element, you don't just insert it at the end. You can insert it in the middle. You can insert it in the middle by disconnecting these next fields and sticking another one right inside and connecting up the next fields again. And so that makes them a lot more flexible in certain ways. All right. So with these programmer created data types, you still would like to be able to iterate through. You still would like to be able to start at one and then go on, and you go next, 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 next. And with the Python built-in data types, you can just use a for and say, you know, you can name the element. Let's say it's a regular list. You name the element, and then you can iterate through, and you get, you know, one element at a time. And Python knows how to iterate. Okay, with a regular old list, it iterates by index. But with these data types that you create, you have to tell it how to iterate. Okay, so that's what we're getting at here. And all this is defined in chapter 18, which is why I'm back here at chapter 18. So when you create an iterator, let's find iterators now. I gotta remember, is iterators, let's see, it's 18. And let's do iterators. So I told you about a linked list. Now here in this little section here, we're actually creating an iterator for a linked list. And these are sort of the characteristics or the properties of an iterator. Okay, so here it's telling you, it's setting you up here. So it's nice to be able to use a for loop. You can use a for loop through a set. Now, so to do this for kind of thing where you're just iterating, it's an object that provides a uniform way for traversing the elements. So in your iterator, in the actual data structure itself, which you've defined, in this case up in the my BST, you have to define a method that looks like this, and it's named. The method is named this, and then in there it's going to return an object of a class that you're going to define, and this is going to be the iterator class. And in this particular example, it defines a linked list iterator, and the linked list iterator is defined here. It's a separate class that's used by it's used by your MyBST in your case. And in this iterator class, all that this thing contains is a variable called current. It's a property called current, and that sort of says where that points, or that's the address that is pointing to the current point in the iterator. Okay, so it's going to start out at the top of this linked list. The first node of a linked list is called the head. So you're going to pass that in, and so that's the starting of the linked list. And then you have to define this next property, or this next method, which when it's invoked, it wants you to return the next element, or the next node in this thing you're iterating. So in other words, it's going to keep track of what the current one is, and it's going to return, it's going to go to the next one, it's going to return that. Actually, the way it works here is the element that it's, first it grabs out the element that it's going to return, and it is the element that current is actually pointing to at that time. Current is always like pointing to the next one. Yes. Well, the current value itself is pointing to the next one. And the reason for that is because you want to know when you are at the end. And so the element that it's going to return, this is a next iterator, and it's returning an element. It's returning a node. The value, the value part of the node. And so that's what it's going to return, and that's why this return element is down here. But before it returns, it resets, it sets this property current, it sets it to the next one. That way, the next time next is called, it already knows that there's nothing left. So then it has to raise this exception. And we talked about exceptions earlier. And basically, it's a special signal saying, we're at the end of the list. You're asking me for something I can't give you because you're asking me for the next element in the list, and there is no next element in the list. So it's an exception. So the exception happens to be called stop iteration. Okay, so basically, every iterator, when you define an iterator, it's got to have these. It's got to have this this initialization thing to start everything up to be the beginning. Once you've defined, you've declared it, and then you have to have this next method, which knows how to it takes the properties of the iterator, where you are, and go to the next one and grab the element out and return that. Okay, so that is that's a little review of iterators. I think that's all I needed to cover in chapter 18. Okay, so let's go to chapter 19. Let's go back to our problem here. And so this is our problem. Actually, I want to go to chapter 19 real quick here and talk about the ways that you can iterate or traverse a binary search tree. Let's see, where might that be? Searching for an element. Let me just go to introduction here. There's 5 different ways that you can search through a binary search tree, and this is stuff that they figured out a long time ago. And so this is talks about how the order of complexity, computational complexity. We don't talk too much about computational complexity in this class. In the next class, 228, we'll revisit all these data structures and talk more about computational complexity, worst case times and all that. But anyway, so here's a binary search tree. This, you should be familiar with this. And where are the traversing representing a binary search tree? Here we're using the same kind of thing as a linked list, except for there's 2 next fields. There's a left next and a right next. Okay, and that gives us this tree structure. And so for traversing the binary search tree, we can do. I want to get to pre-order, in order, post order, inserting. Pre-traversal. There's in order, post order, pre-order, depth first, and breadth first. In order is the one that we're interested in. That's alphabetical. Okay. So if you click on in order here, you can see that the in order is alphabetical. It goes down the tree, and it goes left until it can't go anymore. Until it goes left till it hits a node that has no children, and it outputs that. And then it goes back up to the node that it came from, and then it goes down the right node, and then keeps on going, going down. And it's not until it returns back up, it's not until it realizes it can't go down farther left anymore that it prints out where it's at. So it's going to print out 45, then it's going to go back here and print out 55, then it's go down to 57. Try to go to the left, there's nothing there. So then it prints 57. Goes to the right, tries to go to the left, nothing there, tries to go to the right, nothing there. So, tries to go to the left, nothing there. Prints 59, tries to go to the right, nothing's there. Goes back up, and anyway, then it comes back, it prints 60, and then it's going to boom, print 67, and then it'll print 100, and then it'll print 101, and then 107. And so this is the in order. Okay, so however we do in order, that's discussed further on. But anyway, we're going to do an in order traversal to actually create a list. The way our approach to this is we are going to actually, in our iterator, we are first going to the first thing in our BST iterator is we're going to create the init, and we're going to create the next, but we're also just going to create a list. We're going to take a snapshot of how the thing is right now, and that's going to be this list. And then we're just going to keep track of where we are in this list. We'll start at the beginning, and we'll just iterate down like it's a normal dumb list, not even a linked list. The advantage of that is it makes our response to next be immediate. It's O of 1. It doesn't need to do anything more. It doesn't need to traverse anything. It's just, it knows right where the next one is. And but the downside is that after we've created the iterator, if we should modify the tree, the iterator is going to have old information because the iterator already created a regular list based on what it was when it was created. So anyway, that's a downside. Turns out that for this particular problem, it's okay. It's okay if we create an iterator and then we don't modify the tree. If we do modify the tree, we have to create another iterator. Okay, so I'm going to start writing some iterator code right here. Okay, so the first thing I'm going to do, let me find my nice iterator notes here. The first thing that you got to put there is the init. So that's going to be def init, and we have to put a self, and the root is going to be like where we are. And so the root is the tree, the head of the tree, the top of the tree that we're at. Now we could be down in the tree a little bit, but it doesn't matter. From our perspective, the root is where you are, and then there's a left subtree and a right subtree. So anyway, that's but in this case, it actually is a root because we're initializing. And then so we're going to do two things. We're going to have we have to have this current self.current, and we have to have a variable property called current, and that's going to be equal to a 0. It's going to start out at 0 because we're going to create a list. Here's creating the list. We're going to create a list, and we're just going to call it list, and it's going to equal to this new method that we still have to write, self dot, and we're going to have to write this method, get list, and it's going to start at the root. So that's our init. Let's write our get list method now. Def get list and self again. We got to put that there, and then we're going to start. We're going to call the starting out point. We're going to call it the root. And so how do we get a list? Well, here we have to do this in order search, and each time we instead of writing out the variable instead of writing it, if we're doing an in order traversal, instead of writing it out, we're going to store it into our list. So so how does our now when we create this list, we can do it. We can use a recursive method, or we can just use we can try to do it non-recursively. It's actually pretty easy to do it recursively because we only have to consider roots where if they're blank. Okay, so let's start writing some code here. If the root is empty, if the tree that we're at is empty, then we can just return, and we're returning a list. We can just return an empty list because there isn't anything there. Okay, next now, if the root, if there is nothing in the left subtree, in other words, if we're at a root, okay, if we're at a root and it's not empty, if there's actually a node there, and so the root is a node, let's look at the left subtree, and if there is no left subtree, then we can go ahead and return the element, display out. We're returning a list, right? The first node of the list is going to be where we are because there's no left subtree. So we can return root, return the element, and then we're going to add to that whatever the right subtree is. Now, it's possible that the right subtree is going to be empty also, but that's okay. This takes care of it. So we're going to return the right. We're going to get the list for the right subtree. And that's how that's going to work. So there's no left subtree. So that means that the node, the returned list is going to start at the top, and then whatever the right subtree is. So that's what that'll do. And so that's if the left subtree is now root right. If that's also none, then we're just going to return so if we get to this point, that means both the left subtree and the right subtree are empty. So then we just need to return. No. If we get to this point, that means the left subtree was not empty. That means there is a left subtree. So we're going to return the left subtree. Then we're going to return the node itself. Now, else, the only reason it would get down here is if there is both a left subtree and a right subtree. If there's both a left subtree and a right subtree, then the first thing you got to do is first you got to traverse the left subtree, then you can return yourself, then you got to traverse the right subtree. So the right subtree. So this is all the cases, and it's something like this. Copy, paste. Oops, gotta put the return in there. And add this onto the end of it. So this is the case where we're at a node and there is a left subtree and there is a right subtree. So we're just going to continue on. We got to go down and get the list for the left subtree. This is the case where there is no left subtree. No, there is a left subtree. So this is the case when there is no left subtree. And then this is the case when there is a left subtree, but there's no right subtree. Okay, so anyway, that's kind of complicated. But anyway, so this is actually all we need for our get list. Okay, let's see. So next we need to add the next method. Okay, so that's going to, once the list has been created, that's just going to increment this. This list is now this list is just a regular old list which you can increment through using indexing, and the current property here, that variable, is going to keep track of where we are on that list. So let's take a look at what our next method will look like. Next self. And all this is going to be is if self.current is less than the length of the list, that's this list here, this list. If the self current is less than, if we are not at the end yet, then we can increment. So we're going to increment the pointer first. Actually, I'm going to do this. ELE equal, this is the element that we're going to return. That would be self dot list self dot current. So that's the one we're returning. I'm calling it ELEM. Okay, element that we're returning. And then we want to increment the self. Before we return it, though, we want to increment this. So the next time we come in, it'll be pointing to the next one. And then we want to return the element. Okay. Now, if if just ELEM, that's this thing we're going to return. Okay. Now, if the self current is greater than or equal to the length, greater than or equal, then we know we're off the end of the list. So we just want to do this raise stop iteration. That. Okay, and that should do it. That's pretty much the end of the BST Iterator. And so okay, so we've got the list. That looks pretty good, I believe. All right, so how do we test this thing? Let's see. I'm going to save this. Let's go back to, I think I logged out here. What's this one? I think. So in chapter 19, project 4, let's see, let's save this, make sure we save it. And here we are. So let's see what it looks like. Okay, good. Enter. Okay, so we are down here. So let's enter this. So what this program does is basically it just reads in this list, creates a binary search tree, and then it traverses it. You see, so it right down here, it declares an empty tree, reads in a bunch of numbers, turns that into a plain old list, and then one by one it inserts it into this tree that we've created, and it uses the insert method that came with the BST, regular BST. And it says that's how many are inserted into the tree. It counts them up, or it displays them back out again. Displays out S. S is what was inputted. And then it's going to traverse them. So it creates an iterator. It creates this iterator using this in my BST. It creates the iterator. And that's what it is. And then it increments through one by one, it iterates through it, printing it out. So let's run this again. And let's enter in a nice long list here that I've created. Copy, paste. And we see that this is the list that was read in. And traversing, it created a list, an ordered list, and then traversed it in order. And no, it created an in order. It traversed it in order, dumped that into a list, and that was for our iterator. And then our iterator iterated through it using this next iterator method and displayed out all of the records in order, as you can see. All right. Okay. I hope that helps you with 19.4. Thanks for watching.